Welcome to this presentation. Today I'm going to provide you some slides describing the results that we achieved on our paper on the influence of optimizers in deep learning based side channel analysis. So this work was done together with Professor Stjepan Picek from TU Delft. So the main contributions of this work, we analyzed the role of different optimizers in side channel attack performance on a masked AES implementation, and we see also how this optimizer, what's the effect of these optimizers on some other hyperparameters. Also, we're going to investigate the impact of two different groups of optimizers, adaptive and stochastic gradient descent optimizers, on multiple layer perceptrons and convolutional neural network architectures on different datasets. So this work provides a very extensive case study of of 8 different optimizers on large and small MLPs and CNNs. So the main context of this work is profiled side channel analysis. So in this case, we have a device A, let's say an AES implementation in the hardware or software, and then we collect a set of profiling traces from this device A, where the key is known and under our control, can be fixed, either fixed or variable key. And then from this set of profiling traces, we used it to train a deep neural network in a supervised learning setting. And this deep neural network can be either an MLP or CNN in our case. And then to test the generalization of this network, we collect another set of traces that we call validation traces, also with known key. And then we see how the trained neural network is performing for this, according to the training that is performed on profiling traces. So in the second phase of the profiled attack, what is called a test phase or exploitation phase, we have a device B that is identical to device A. And we also collect a set of traces. In this case, we call attack traces, where the key is either unknown if this is an attack from an attacker perspective, or the key is known if it's from evaluator perspective. And then these attack traces are fed into the neural network and they are predicted. And the output of this network would be probabilities indicating if we are recovering correctly the key associated to the attack traces or not. So if we are able to recover the key, we say that we have a good generalization in this trained deep neural network. So what we have seen recently in the application of deep learning to profile side channel analysis is that a lot of efforts in terms of pre-processing for side channel traces before the attack phase is moved to the effort on the side of hyperparameter tuning phase. So side channel pre-processing can be either alignment, filtering, points of interest selection mainly. So then all these parts are not really necessary, strictly necessary when you're using deep learning. So because this process is automatically done by the neural network. So the hyperparameter tuning effort now requires quite some attention. And then to know how to tune your hyperparameters, you need to have knowledge about specific hyperparameters. And then even if you're using an automated search on your training process, like letting the algorithm to decide for you what are the best hyperparameters for that attack scenario, then even then you need in random search or grid search or optimized search, you still need to define ranges or optimal ranges for hyperparameters. This means that you need to decide how many layers you want to search, how many neurons per layer you are going to search, what are the activation functions, or also in convolution layers, how many filters you are using, and etc. Besides all these constructive aspects of the network that are hyperparameters, we also have extra parameters that we need to tune, which are related to the training phase. Let's say how long the training will take, how many epochs, the batch size to process each iteration, also the learning rate, the regularization aspect, initializers for the array of weights, and also very important, the optimizer that to train your neural network. So in this work, we focus mainly on the relationship between optimizer and the training time, the amount of epochs to train the neural network, and how the attack performance behaves when you have different combinations of these parameters. Okay, so one very common question is how long to train a neural network for side channel analysis. So it always depends, and let's say as a motivation for this work, we start to analyze different neural network size when we fixed one optimizer, and then we train this many different neural network models of course, for fixing the optimizers to RMS propagation, and we train it for all these models for 500 epochs, and at each epoch we computed guessing entropy for the attack set. So you can already imagine that this process is very expensive. So, but what we wanted to see is how the guessing entropy, what is the guessing entropy value typically for different neural network sizes at different training times. So then we saw that mainly for smaller models, the gas entropy tends to be very small. When you have blue color here, it means the gas entropy is small, and when you have green color, it means gas entropy is around random guessing 128. Sorry, and then we observe that for smaller models, the gas entropy tends to be smaller. Or on the other hand, for bigger models, the gas entropy tends to be high. So then we changed the optimizer to SGD, and then we observe a very different behavior in this time. Let's say for bigger models, the gas entropy is smaller, and at the same time for smaller models, gas entropy is not very good. So then we decide, okay, optimizers change completely the scenario of the attack of the training process, and then they deserve some more close analysis, of more attention to understand how they really impact the training phase. Besides that, we also have other, let's say, quantities to analyze. Let's say number of profiling traces, if we are using or not a regularization. So this always, all these elements affect also the training capacity of the network. So regularization is not the main topic of this paper, but it's important to know the types of regularization and when we need a regularization to understand also if the optimizer is able to provide, is requiring or not a regularization in this case. So let's say regularization can be divided into implicit regularization, which is a case when we have, more typically the case when we have a small model and a large training set, because in this case the network has small capacity to fit the data, which will provide, of course, less overfitting. And if usually also it happens when you have small learning rates. So implicit regularization is a sort of natural regularization that the network provides during the training phase because it has less capacity by its shape itself. So you can also add explicit regularizations, and this is more convenient when you have large models and small training sets, because then you can overfit easily. And then explicit regularization are basically extra options of regularization that you can add to the neural network configuration or the training configuration in order to prevent the overfitting. And what we have observed in this analysis, in this work, is that the choice and also the understanding of the optimizer behavior helps a lot deciding when and if we need regularization and which type of regularization we need during the training process. So what are optimizers? So if we have a neural network, let's say, with input, hidden output layers, and we we feed this network with side channel traces labeled according to a specific class, and then the output of this network will be class probabilities indicating how likely a trace belongs to a certain class. And then there is a loss function that is computed from the expected prediction and the actual predictions. And for side channel analysis, we commonly use categorical cross entropy. And this loss function is used then to update the array of weight connection, the learnable parameters during the training phase. So what we can say is that training a neural network is basically learn all this array of parameters, including the bias for each layer. So the optimizer is basically the equation that makes this weight update. So optimizer is then combines learning rate and loss function in this update process. And as we see in this work, because we analyze different optimizers, the optimizer equation can come in, with different equation with extra parameters, not only learning rate and the loss function. So I said in the introduction, we analyze two classes of optimizers that are divided into adaptive optimizers and SGD optimizers. So adaptive optimizers that we analyze are ADAM, RMS propagation, ADA-grad, and ADA-delta. So these optimizers, they basically adapt the learning rate during the training process. For example, ADA-grad will adapt the learning rate according to the features of the data, for example. And different optimizers will require also different parameters, but in this case, let's say beta 1 or 2, these parameters also can be provided by the user, but we set these parameters as the default value from TensorFlow library. On the other hand, we have SGD optimizers, and then we analyze 4 classes of these SGD optimizers. Without momentum and with momentum, and also combining with nested-of. So momentum is a way to accelerate the SGD convergence during the training phase, and nested-of is a method that will prevent the momentum for going too fast. It's a compensation that prevents it going too fast during the training process. So here in this slide, I will discuss the typical behavior that we see in related works and also in our experience with this topic when we are conducting an attack. So in order to have a successful attack, when you are measuring the guessing entropy of one attack byte, you set, let's say, 200 epochs, and then you start your training process. And then after processing 200 epochs, you collect what is the guessing entropy of your attack set. And then you ignore what happens before 200 epochs and you only look for the result at 200 epochs. If the guessing entropy is 0, it means that your attack is successful. But the scenario can also be a bit different. Let's say you train the network, and then what you get is a bit higher guessing entropy at the end. But if you would be able to see what is the guessing entropy evolution during the training phase, you would see that sometimes it happens that it decreases quite fast, and then maybe converging to the guessing entropy 0, but then it's after some amount of epochs it starts to increase again. So this means that this means that in this scenario you can have overfitting of your neural network, and then one thing you can do is to add some sort of extra regularization, for example, early stopping, to stop the training when you observe let's say the lowest guessing entropy. Of course, this can be very expensive because you need an extra metric computed for each epoch of your training phase. And guessing entropy for each epoch can be a bit expensive in terms of time. Another option that can be a bit cheaper is to add other types of regularization, for example, noisy layers or data augmentation, to actually prevent the overfitting to happen. So the network will not overfit anymore because it will not learn too much. The training set, to memorize the training set after some certain amount of epochs, and then the generalization will stay at the same level even if you process more epochs than you need. So what I'm going to show you in the next slides in the results experimental part is that knowing the optimizers that you are using in your training phase will help a lot predicting the behavior of your network. And then you can decide beforehand which type of regularization you need to add, or if you need smaller model, bigger models for your training phase. Sorry. So the data sets that we use in our empirical validation process is ASCAD dataset, and this link provides you where to get them. And we have two ASCAD datasets that we use, fixed key and random key. So the first one contains 50,000 profiling traces and 10,000 attack traces. The second one is contains random keys in the profiling set with 200,000 traces and 100,000 traces for attack traces. So the trace interval represents the processing of key bytes 3 in the S-box output of the first encryption round. So the methodology that we use in this analysis is the following. In the first moment, we generate random MLPs and CNNs, and we split these randomly generated neural networks into small and large models. So small model would be any model that contains less than 400,000 trainable parameters, and a large model would be any model that contains more than 1 million trainable parameters. And then we're going to analyze the typical behavior of optimizers against these two different groups of neural networks. And the second part, we define specific models, fixed hyperparameters, either small or large MLPs and CNNs. And we are also going to see if we can confirm that the typical behavior that we observe randomly for different hyperparameters can be also seen in specific models. And we evaluate all these scenarios on these two data sets. We always trained the neural networks for 500 epochs, and we test always 8 different optimizers. And also for each epoch, during each training process, we compute the guessing entropy of correct key bytes of the correct key byte by processing 2,000 attack traces. So here I have the results of the typical behavior of adaptive optimizers when we train them on small and large models. So every guessing entropy line in this plot, in these 4 plots, they show the average of 1,000 guessing entropy calculations on randomly generated models. So what we can immediately see here is that RMS propagation and Adam optimizer, they show some sort of similar behavior in a way that guessing entropy decreases very fast very early in the training phase, and then for both combination of small or large models, they start to degrade a little bit, and this increase in the guessing entropy is a bit higher for large models than for small models, and this is expected because in the large model case you have more overfitting. And on the other hand, small models, they show very poor performance, I would say, for the ADA-grad and ADA-delta, but the convergence is a bit better when you have large models for these two optimizers. So for SGD optimizers, we see that when we have momentum in the training process, the convergence is faster as expected because momentum should provide this behavior. And for when we don't have it, we also have the convergence, but a bit slower. And again, we see that smaller models, they show less overfitting compared to large models after a certain part of the training process. So adaptive optimizers on specific models, let's say small models, small MLPs and small CNNs, they show similar behavior of what we saw according to randomly generated neural networks. But this time we can see that, of course, this is a specific model which contains specific behavior, but it is again aligning to what we expect in general. So we have for Adam and RMS propagation, we have the fast convergence of the guessing entropy up to a very low value, and then either it stays low but increasing a little bit the value, or increasing a lot when you have CNNs in most of the case. So we can see that when the gassing entropy increases after it reaches the minimum value, we have very likely overfitting, and this is more often for CNNs because CNNs they have more capacity than MLP to fit the data. And also we observe that ADA delta and ADA grad, they don't show very good behavior for small models on adaptive optimizers. So here we have a lot of results for large models. So in this part we have large models for MLPs and large models for CNNs. And for this scenario on the 4 adaptive optimizers, we can observe that for large models we also see the fast convergence for ADA and RMS propagation when we have MLPs more than we have CNNs. And after they can overfit quite a lot, and gassing entropy can increase quite a lot up to a level that is almost close to random gassing. So, but what we observed in this case is that for large models and large data sets, which is the case of ASCAD random keys, ADA grad behaves quite well. So the convergence can be very fast. You see before 100 epochs, it's already very low, and the overfitting almost doesn't happen. So the interesting observation here in this slide is that ADA grad in the scenario when you have large models and large data sets can be a very convenient choice for side-channel analysis. So specific models for SGD optimizers and small models, we observe again that momentum is needed in order to have a faster convergence. And also the amount of overfitting with SGD with momentum is not really as big as when we have ADAM and RMS propagation, which also provides faster convergence but more overfit. We see overfitting, but it's not in all the scenarios. Mostly when you have more data, is not really clear why exactly more data led to overfitting here, but the network behavior better when you have a smaller data set and smaller amount of small capacity in the training set. So I will discuss a little bit later about this effect of having more data is always better or not. So here is a scenario when we see a more particular behavior of the gassing entropy against this optimizer, SGD optimizer. And we see that mostly for the case when you have more data and so large MLPs and for a smaller data set shows a strange behavior here. But when we have more data and large capacity, which is large CNNs and large MLPs, we see that there is a decrease in the gassing entropy to further have an increase and then a decrease again. So this behavior was a surprise in that we saw that there is a very recent paper describing this phenomenon that is called deep double descent. So the authors of this paper basically have shown that more data or larger models usually don't provide better performance. So they show that there is the effect when the training error. For our case, we use gassing entropy as the metric, not the loss or the error function. But we can make a parallel here in terms of behavior. We see also that in their paper they observe a decrease, an increase, and a decrease again. And also in the red line here, they showed a very similar behavior to what we observed in our large model here. There is a decrease in the error function, an increase, and then the decrease again. And we are minimizing the gassing entropy, and also we see this effect. A decrease in gassing entropy, an increase, and a decrease again. And this happens specifically when you had momentum in the SGD training phase. So what we can conclude from this analysis is that more data and larger models or larger training phases usually are not always beneficial for side channel analysis. So there is a combination of elements that needs to be carefully selected when you're doing your process evaluation. And knowing what each optimizer can offer in terms of behavior can help a lot on that process. So the main conclusions of this work are the following. Adam and RMS propagation, they easily overfit, especially for large models, and the training phase must be short or combine it with explicit regularization in order to avoid the easily or the early overfitting that can happen for these two optimizers. So I would say early stopping with a specific metric or even some other type of regularization, data augmentation, etc., can help this process. Another takeaway is that AdaGrad can show very good behavior in large models and large datasets, large training process. So it's a very good alternative if you're using adaptive optimizer to use AdaGrad, because it can really show less overfitting compared to other optimizers. SGD with momentum is the option because it provides also less overfitting and faster convergence than without momentum, and also we saw that there is it's comparable to the behavior, to the performance of Adam and RMS propagation, which are very common choices in side channel analysis. So also then we saw that the effect that sometimes the gassing entropy starts to increase and decrease again, it's already reported in the literature, and it's called deep double descent. And what we can mainly conclude from this analysis is that more it's not always the better. So for sidechain analysis, we can also assume that small models can work relatively well. So thank you for watching this presentation. If you have any questions, do not hesitate to send me an email.